Hi students, welcome on this lecture on the spherical coordinate systems. So in this lecture we are going to learn about the spherical coordinate system, and we will also learn about how do we calculate the solid angle because of part of the spherical surface. So like in Cartesian coordinate system or the coordinate system which we study in our 11th, 12th or the 10th class, we take x-axis, y-axis and the z-axis, and with the help of these x, y, z axis, we give the coordinate of a point like x, y, and z. These coordinate are the unique coordinate for any unique point in the space from a origin, from a random point which we take it as a reference, right? And like that we give every point will have its unique coordinates, and with the help of these unique coordinates we can find out the location of that point. Now what happens in spherical coordinate system is that instead of using the xyz, we are using three different coordinate r, phi and theta. Okay, with the help of these three coordinate we will be able to identify any point in this space, and that point will have its unique coordinate, unique spherical coordinate. Okay, so what is r? R is the, let us suppose we take it as a reference point. So r is the distance of that point from this reference point. And what is the phi? So for that we have chosen a axis. You can give any name to this axis, like let me just highlight. So here I have taken this axis. I have just given it as x-axis name, or it is any line. So from that line there is the, you also take a plane like this in the, and then there is another line. These are basically three perpendicular line from each other. Then this line projection, if you take like this, okay, so this projection will have a certain angle with that axis, that is phi, and then this line will have some angle with this vertical axis, that is theta. So these are r, theta and phi. Okay, so in our 11th and 12th, where do we use these spherical coordinate system? Generally, like we'll use for the calculation of the flux, or we will calculate the maybe luminous intensity, and from that we'll calculate the power, number of photons, and sometime even we can use this for the calculation of the center of mass, moment of inertia, and like those things, and force on the surface, torque on the surface, all those things we can use. Okay, but we'll generally use this spherical coordinate system for the calculation of the flux, and especially flux through a disk, because of a point charge. That is a important application of this spherical coordinate system and the solid angle. So of course we'll study that in this lecture alone. So yeah, now like if I want to create any 2D surface, let us suppose I want to create a surface like this, then I will have a little variation. Let us suppose this is x direction, so I will have a variation in x direction, let us suppose dx, and let us suppose that direction is y, so then this direction will have a little variation dy, and the multiplication of both of that are going to give us this surface which is dx times of dy. Okay, the surface area becomes dx time of dy. So like if I want to create any kind of surface, basically I have this Cartesian coordinate system xyz. In that any of the two coordinate I will change, and with this help of these two coordinates I can create any surface, because any surface will have two dimensions, two different directions and two different sides. Okay, so how do we create the surface in the spherical coordinate system? So what will happen here, we have three coordinates. We have r, and then we have phi, and then we have theta. Then if I change r, then I will be able to have a linear length like this. Okay, elemental change if I take, so then the elemental change in the r is dr. Okay, When I change this angle theta, let me just denote it here. So I change this theta like this slightly, then I will be able to create a linear length. Okay, I will be able to create a linear length. Okay, here, this kind of curve, this one, and because this is d theta and this length is r, so that's why this becomes r d theta. Okay, so theta if you change, so then it becomes r d theta. And if you change angle phi, so first of all we need to calculate this length so that we can find out the arc length, and that becomes r sine theta. Okay, so that is r sine theta, this length of, because we are taking the projection of this on the horizontal plane. So if you remember the projection, the direction towards that we have theta in that direction, the component is cos component, and perpendicular to that we have sine component. So here we are having sine component because we are taking the perpendicular projection. Okay, so this is that arc like this, and that arc length is r sine theta d phi. Okay, let me just write it. So that is r sine theta and d phi. So we have dr, we have r sine theta d phi, and r d theta. Okay, if you multiply any of these two, then we will be able to create the surface. Now in case of spherical surface, generally r is constant, so it means theta and phi are changing and they will combine and they will create a elemental surface. So I just, if I want to denote it, I can say something like this, that like this will have a elemental surface in case when the r is constant. And that elemental surface area, when the r is constant for any spherical surface, is the product of these. So that is r sine theta d phi, r sine theta d phi, and r d theta. Okay, so that becomes r square sine theta d theta and d phi. Okay, we'll mostly use this. Sometime maybe we can also change the r and we can change another phi maybe. Then we'll have the another surface area which you can multiply and you can find out elemental surface area, or otherwise we can have variation in the r and we can have variation in the theta. But that is very limited application, so that is why we are not going to go in that. And we can also find out the elemental volume, which is the, like, if I want to create a elemental volume, basically I will change all of these three. X-axis I will change, y-axis I will change, and the z-axis I will change. So I will have a little variation in x-axis, a little variation in the y-axis, and the little variation in the z-axis, which gives us the elemental volume. You can say dx, dy, dz. This is for our Cartesian coordinate system. So here also we can have the volume, but that also will hardly use. So let me just write down the expression, maybe you can use that. So that is r square sine theta d theta and d phi and dr. This is the elemental volume which we create with the help of the spherical coordinate system. Okay, all right. Now why at all we are studying this is because we want to find out the flux, because of a on a disk, flux crossing on a disk because of the point charge that we want to find out. Okay, so basically it means we want to find out the solid angle of the disk. So let me just take somewhere here. So something like this we have, maybe. Okay, and here we have a disk like this. Okay, so this is a disk like this. Okay. Hmm. Okay. This is a disk like this, and I'm taking that, let us suppose this disk, if we connect it from the center, this distance is maybe small r. Okay. This distance is, let us suppose, a small r. This angle is, let us suppose, theta naught. Okay. And we want to find out the solid angle. So this is the discussion on the solid angle calculation. So first of all, we need to go to the solid angle definition and how do we calculate very basic formula of the solid angle. So this solid angle, like the angle we define, angle is length of arc divided by radius of arc. Likewise, let us suppose if you got a surface like this, a surface like that, and the surface area of this surface is something dA, a very elemental surface. So then this surface will have some angle here in the 3D, okay, some kind of quantity that is, we denote it with omega, that is dA divided by r square. R is the distance of any point on this surface from that point. And if we take a elemental surface, almost all the point will have the same distance. So here also you might think that okay, so what is the problem? We can find out the area, this area, okay, whatever the disk area is there, and you can just divide it with the r square. But that is not that area we are talking about. We are talking about the area which has all the points, or the all complete area which has the same distance from that. Basically, this disk is somewhere inside this sphere. Okay, if you look in 3D, so then maybe I can say it like this, that okay, and this is a, suppose that this is a sphere. So let me, so first let me reduce the side of this sphere. So okay, fine. So yeah, okay, something like this. So if you fit this disk in the sphere, then the basically this much area of this sphere, and if you take the projection of this, then whatever the area of this surface is there, this disk is there, the same area this is also having. So that area we need to count here. Basically the area of the surface, this complete surface of uh, this solid sphere, that we need to count. Okay, that area we need to take. Basically area of this cap, we'll call it as the area of cap. So we need to find out that area of cap. So how do we calculate? All the points on that area of the cap are at a constant distance, so we'll apply this formula. So we have this formula, dA is equals to r square sine theta d theta and d phi. Okay, so total surface area is integration of dA, which is r square is just a constant, and then we have the sine theta d theta integration and the integration of the d phi. Okay, phi is the angle of the projection, so maybe you can take the angle like this. So now you need to understand the limits here. So phi will vary like this, and if you want to touch all the points on this cap, then you need to vary this phi from the 0 to 2 pi. Whereas the theta will be variable just from the 0 to theta naught, then you will be able to touch all the points through like this. And because you are varying this phi from the 0 to 2 pi, so that is how you will be able to also cover these points. Okay, so that is why this theta is from 0 to theta naught. So then that surface area becomes A equals to d phi integration is phi, and the limit if you put 2 pi, so then that becomes 2 pi r square, and the sine theta integration is minus cos theta, and if you put the limit, just change the limit and 0 will become 1, so 1 minus cos phi naught. This is the area of this cap. You can keep even this area in the mind. Okay, just memorize it. Now let us come to this solid angle again. So solid angle is the surface area of the sphere divided by r square, that is 2 pi r square 1 minus cos phi naught divided by r square. So r square is cancelled out. So basically we get 2 pi 1 minus cos phi naught. Okay, so this solid angle also you can memorize, that this is 2 pi 1 minus cos phi naught, and phi naught is the angle, okay, of this disc end. Okay, so that is the solid angle, and this solid angle we can use. One more thing you should keep in mind is the solid angle because of the complete sphere. This is because of the cap. This is the solid angle of cap. Okay, for complete sphere, we'll say solid angle is A divided by r square. And what is the surface area of this complete sphere? That is 4 pi r square divided by r square. So that is why the solid angle becomes 4 pi. And unit you already know that it is steradian. So this is the solid angle for the complete sphere, and this is the solid angle for this cap. So this is a mathematical concept. This I want to introduce this to you. You can learn it maybe more in detail through these some other videos as well. Or otherwise just request me what you want to learn. Maybe I will make the video on that. And I have also done some mathematical topics on this channel, like the integration, differentiation, and there are the also other lectures on the other topics, and on the physics, maybe it is electrostatics, capacitor, or anywhere. You can learn that very well on this channel, STEM with DK Swami, and you can subscribe this channel and share this video with your friends. Thank you very much.